Okay, so I'm continuing on with this decision analysis example. Right? We're in the middle of just starting an example. So let's say I've collected some money to be invested, or promises of money to be invested, amounting to $10 million, and I need to decide whether to launch the satellite, delay for a month expecting more favorable conditions, or just to abort the project. So which of those three choices should I make? Well, of course, I want to optimize the return on the investment, right? So let's take a look at this. First of all, the probability of a success based on perhaps historical data and other variables involved. The best estimate is 90%. If I wait a month, that probability goes up for a variety of reasons. Profits, if I launch now, the profits are $20 million. If I launch next month, the profits are only $10 million. However, there's a chance of failure, a small one, but there's a chance of failure. And if we fail, it's going to cost us $120 million. So I want to know what should I do here, including possibly walk away. So the decisions are, should I launch now? Should I launch in a month? Or should I abort and forget about it? It's a $120 million loss. And the uncertainties, of course, are the probabilities of success or failure. And I forgot I left this stupid little thing in here. Don't worry about that. So my decision at the beginning is to either launch, wait a month, or abort. Right? And depending upon what I do here, I have a chance variable involved for each one. And the probability of success, if I launch, the probability of success is 0.9. The probability of failure is 0.1. Similarly, if I wait a month, the chances of success are higher and the failure is lower. And if I abort, it costs me $10 million. If I just forget about it, it costs me $10 million. I don't get the 10 mil. So the profit here, as I've said, if I launch now, the profits are $20 million. Failure is 120 million. Chances are low, but that's a possibility. Here, the profits, if I wait a month and I'm successful, my profits are $10 million. And of course, the same cost for failure. So now I can calculate what is the expected value for each of these decisions based upon these numbers here. So the expected value of my launch decision is 0.9 times the profit plus 0.1 times the cost, $6 million. If I wait a month, my expected value is 0.95 times the profit plus 0.05 times the cost. That's $3.5 million. And then, of course, the expected value of an abortion, an aborted mission, I should say, is $10 million. Negative. Okay, so the best choice, it looks like, based on these numbers, is, in the simplistic example, is $6 million. And I should launch right now. Okay. So I have another more complete example. This is from some project in China, Shanghai, China, for a municipal power infrastructure. And it's somewhat simplistic, but so they're looking at, should I choose a large coal plant a large natural gas plant or some flexible natural gas plant. Right? So if the demand is high, the probability of demand being high is 0.5. Demand low is 0.5. Demand high, demand low. So that's a chance, right? Probability of production being high, production being low, and so on. And I forget what this R means. Anyway, it doesn't really matter, but it's a chance of something happening, right? And these are the present values or the expected values of each of these paths, right? So, for example, if I choose a large coal plant and the demand is high, right, well, there's a chance of, I don't even know what, as I said, I don't know what this means, but there's a 20% chance here and a 80% chance here. Here are the values for this situation, and here's the expected value. What this expected value is just the weighted average of these, right? 0.2 times 38, 0.8 times 212. That's that. Right? Same here. 0.5 times 94, 0.5 times 138. Added together. Okay, so down here I've got so I've got a couple of decision points here, right? These are, they're single decisions, so it's not very complicated. But down here I've got some flexibility built in. So I am choosing a flexible natural gas plant, and I have a choice, or I have a chance that the demand will be high or low, right? 50-50. But if it's a high demand, I have another choice to make, a decision to make, I should say, because it's a big D. Should I add 300 megawatts capability or not? And if I do, again, there's a probability of high and low demand. Similarly here, high and low demand if I make no addition, right? And so here's the expected value of this path. Here's the expected value of that path. So the expected value of the two is this, of these two is this, and so on. And see now what this allows me to do here. I can pick the highest of these four, two of the highest of these four, to represent the value, the expected value of each of these decisions. So the expected value of these decisions, this one, is the higher of these two, and of this one is the higher of these two. And then back here, again, so if I have an expected value here and here, 50-50 chance, this number, 98, represents 0.5 times this plus 0.5 times that. So that's how I would get the expected value of each choice. Similar to what I did with the raincoat, except it's a little more complicated, that's all. So actually, I think the large coal is 94, right? Right here. The expected value of the large natural gas with high demand is 116. Where did I? Oh, right here. Yeah. Okay. So that's this one. So the large natural gas with high demand is this average. Similarly, down here with low demand is this average. So the expected value of the natural gas option is just 0.5 times that plus 0.5 times that. I can do this. I could do the same thing with the garage case, right? I mean, I could do the fixed, staged, or flexible plan, or even more, right? All right, so that was almost 10 minutes. So let me wait on dynamic programming, and I'll have one more video.